Hi guys, welcome to the fourth part in this video series on writing a bare minimum chess program in C. And in this part we're gonna talk about how how do the search and the evaluation work in this chess program. And the name for the algorithms involved here are the Nigamax search with the alphabet Patron. And to have more information about this particular algorithms, you could read this brilliant explanations by Bruce Morland. I'll put the links to these pages in the description below the video as always. And this is for the Nigamax function, and this one for the alphabet Patron algorithm. And I just briefly explain what this does. What is the alphabet Patron? What's the difference? The Nigamax search is a kind of brute force algorithm, and this means that he looks to every single move available in the chessboard, and he looks also for the dump moves which are not really good to play, but they are still evaluated. And what the alphabet search, alphabet Patron or alphabet search does, he finds those moves that are not really that clever, and he just makes some pruning. So he makes some cutoffs of the branches that are not really, like in human perspective, worth of evaluation. And how particularly is this working is described in these pages, and there are also lots of YouTube videos about about the alphabet algorithm. And I'm not really good at algorithms, especially in understanding them in great details. I just only know how to make some use of them, so the application of this particular algorithms is involved in bare minimum chess program we're writing now. So let's go. We have to define a few more variables. The first is the piece weights, and this is the array storing the values, the relative values of the pieces, of the chess pieces. You know, like when you play chess, you know that say the knight is worth of 3 pawns, and 2 knights are worth of 1 rook, or maybe knight and bishop is worth rook. It depends on how you initialize this array, and this actually does kinda change the behavior of the engine. So changing these values might slightly change the style of the bare minimum chess program play, so it can change its style. And these two variables are the best source and best destination. It's used to store the best move corresponding to the best square that is returned by the search function. And now in the search function, here we add 2 more arguments, the alpha and the beta, which would store the best score for the maximizing score side as well as the minimizing. So one is maximizing, other is minimizing. And now at the depth of 0, instead of just returning from the function, from the recursive calls, we have to evaluate the position of the leaf node we have reached. So here we initialize another variable. So this is the material score, the positional score, the piece, and the entire evaluation. Then we loop over all of the board squares, look for only those that are on board. Then we initialize the piece, and then we calculate the material score via lookup in the piece weights array. And the piece weights array memory map is the same as the memory map for this pieces array to represent the pieces on board. So this is just the same. We use the same indexes as we did over there, and we also have the bitwise end, this value with 15, just like we did in our here, like we did in our print board function. So absolutely the same way to find the reasonable index. And then the interesting thing, another interesting thing is how do we evaluate the positional score. So if after bitwise AND and our pace was 8, we find the value of the true value, then what we have to do is just add to the current to the variable of the positional score the value of current of content of square plus 8 on the board. And this is very interesting. For this is actually where this part of the board array becomes handy. So say we want to give the evaluation of this pawn, which stays on square h2, yeah, and when we add 8 to this square index, we will find the value of 5. So this pawn standing on h2 scores the value of 5. So if the pawn is going to stand on e4, it would score 30, and so on. And that's how the piece placement is associated with the score. And this particular values are needed to give the computer an idea of how to develop his pieces towards the center. So that's very important. And now and another thing to mention is that changing this value also affects the behavior of the chess program. So it would play completely different variations if you change this value. So try to play around with this. It's really interesting. It was the very first thing I've used to do when I didn't know how to code, but I already was looking at somebody's source code of chess programs, and I really did like to play around with these values, and to see how the behavior of playing style is being changed. And now let's see the algorithm itself. So we define another some another variables, and it would become more clear while I'll be explaining what are they needed for. So we go down, and the line that has changed since the previous video is this one, the recursive call. This minuses here is known as the Nigamax framework, and again this is explained in great details over here, so please take a look. I'm not really good at explanation. I don't understand this to my own somehow. I know how to practically apply this, but I can't really explain this well, so just please reference the link that I give you in the description. And in order to store in order to detect the checkmate, we have to store the best source and the best destination square just before any other scoring, and this comes handy when the entire function has returned a plus infinity represented by 10,000s, and so like no move to be evaluated. And if we don't add these two numbers, and if we don't store the move that has resulted the king capture, then we actually would have no idea of what move was that, and it won't be stored in this part where the best move is usually stored. So storing the move, it seems like we're storing the first move, but it is actually so, but in any case is not that doesn't cause the king capture. This would be overwritten over here, but in case of the king capture it won't be actually overwritten. So this best source and best destination square would store exactly the move that has caused the checkmating, and that's very important. And now the alpha beta stuff. So again, the alpha beta algorithm is described very nicely over here. Let me just restart the timer again. I don't really want this video to go on for ages like the previous one. It has been encoded for about 3 hours in my little Asus laptop. That's a pain, real. And the idea behind this is that if the score that the move has gained after the recursive call is bigger compared to the score that is stored in alpha, or in this case the alpha acts like a max in minimax. So like alpha is see alpha as the best score. So if the current score is bigger than the best score so far that was founded, then alpha is equal to the score that we have just gathered over here. So we increase the value of the best score each time we found the better move. Well, that's the right explanation probably. And also to make some associations with the score and the move, we have to store the temporary source and temporary destination squares, and these variables are defined in the search function, so they are kind of local ones. And finally, when the function returns the best move in the like given depth, yeah, this happens over here, and here we actually use the global variables for storing the best source and best destination squares as well. Well, these are also being overwritten along the search works. For the best move on depth 1 might not be the best move on depth 2 or depth 3. So this is incrementally updated. But when the entire function of search position returns its final value, well, it's still stored in the best source and the best destination, and this is used as the reference to make the move. Yeah, and at the end of this function we also return the alpha, which is the best score basically. And this just associates the particular move to the best score. And now a little driver program to just to test all of these algorithms. And what we do here, we define the depth. It's just to be more convenient way of calling the function. Also we define the site, we print the board, and these two lines and this one here is used by a single command in this debug constant. This code is not going to be executed, so it becomes handy when we want the program at the debugging stage to have two behaviors, like one when the computer plays itself and another when it plays with the user. But now we're not going to actually command this, for we want the computer to play against itself. And what happens here, we are in the infinite loop where computer plays against itself, and each iteration of this loop we want to know the score for the position, and we call actually the search position function with the values of minus infinity and plus infinity, represented by minus 10,000 and plus 10,000. And why is this so? Again, you please reference over here in the alpha beta stuff. And then, as far as the best move has been stored over here, it is now done, and it's now done on the board. So we clear the destinations, so the board destination square now equals to board source square content, so the piece moves, and the square, or the source square, is cleared. And then we change the site exactly the same as we did this in recursive call. So 24 minus 16 is 8, 24 minus 8 is 16, so the site has been changed from black to white, and on the contrary. And then we want to print the board with the move that has been made, and print the score and print the best move, and wait for the user input to make user able to see each particular move of the game. And now let me just quickly demonstrate you how this works. So the white is playing d4, d5, and as far as we are at the depth 1, the computer plays very dumb moves. So now he would capture the pawn on d4 with the queen, for he thinks he's going to be better after, and he can't see that the queen would be recaptured, and this is now known as the horizon effect. See, now computer thinks that black is actually better, but it's not really like so. After the queen has been captured, so at depth 1 it's not really look like chess. So that's why we have to increase the depth, and as far as we are starting to increase the depth, the computer is starting to play a little bit more reasonable chess, and you can see that already at the depth 2 it actually looks like it's playing chess. If you increase the depth a little bit more, say to depth 3, that it would look like almost like a normal chess game between two engines. Well, basically this engine is playing itself, but nevertheless. So this is how it looks like in action. So that's the result output of our search of our Nigamax search function with the alpha beta pronin, and this score goes a bit crazy, and again this happens because of the horizon effect. So the computer can't see the true result of his move because of lack of the quiescent search, and the quiescent search is a nice technique that allow you to keep searching the position, so keep diving into the position and creating new branches until the quiet position is reached. I mean, just when everything has been recaptured and no forcing moves are available in the position, so only the quiet moves, so no captures and no checks. Well, sometimes the checks are also considered to be forcing moves. Well, basically they are, but not every engine implementation checks for the king in the quiescent search. Well, but as far as we're writing the bare minimum chess program, not the real one, we'll omit the quiescent search. So that's kind of the end result. And the last thing we want to add is some sort of user interaction. So we would make it possible for user to enter the moves, and then the computer would respond, and that would basically be the already finished project. So the next video is going to be the last in this series related to the theoretical and practical moments, and the video after this I'm going to play against bare minimum chess program myself, and that would be probably a lot of fun to see if I would be able to beat the program that I've written myself. And so let's see what happens. See you next video, guys. Bye.